Sorularsa var mı? Sol amperler.
Well, okay, the question that I was expecting for the last 2 hours finally arrived. So are these questions involved in the exam? Everything we do until Saturday will be included in the exam, including what you discuss on tomorrow's recitations.
Hocam bir şey soruları ne zaman yazıyorsunuz?
Sometime before the exam. If you think that I will not be changing the questions, I haven't prepared them yet. So, okay, let's go back to the question. If you remember the question, how does the electric field know that there is zero resistance in one direction so that all the electric field lines go through that point? I mean, in this question, if R2 is 0, we said that all the electric field lines are passing through here. There is no electric field line passing through R1. If this is a zero resistance piece. And so all the current will be running through here. So how does the current decide which way to go? Now let's go back to our first discussions about the batteries and the currents, what's actually happening. Now we have this battery. We said that the battery, let's imagine these are the contacts. This is positive, this is negative. Now the battery doesn't really create a potential difference. It takes electrons here, gives out electrons from this terminal and takes away electrons from the positive terminal and hence creates a potential. So there will be electrons leaving this and there will be electrons absorbed by the positive terminal. So there is no conductor here, nothing. You can just imagine that this is just the parallel plates. So what will happen when we turn on the battery? Yeah, there will be negative charges accumulated here and positive charges accumulating here. So this is what the battery does. Now let's imagine we put a conductor over there. It's in contact. Now, what's a conductor? A conductor, we said that it's a material in which the charges can move. But of course, in different types of conductors, it will take a different amount, the charges will be moving with different ease or difficulty. Or if this is very long, it will take the charges a long time to go from one end to the other end. But what will happen is, okay, there was positive charges over here and negative charges over here. So they will be, the electrons will be moving from the negative side to the positive side through this conductor. But let's just imagine that the drift velocity is very small. So it takes a very long time for one electron to go from here to over there. But the battery just keeps pumping electrons. So there are more and more electrons are coming over here. So this plate will be charged more and more positively. That means there will be a larger and larger electric field building up in this conductor. If there is a larger and larger electric field building on this conductor, we are pushing the electrons in the conductor with a larger and larger force. That means the drift velocity will become larger and larger. And this will continue until the drift velocity will be taking electrons from one side to the other side. So the electric field will increase and increase until the drift velocity becomes such that for each electron that leaves the battery and comes here, there will be one electron that passes from this side to the other side. And after that point, there is some accumulation of charges at the ends of my battery, my conductor, because I connected it to battery. The electric field is building up, it's increasing. So the drift velocity is increasing and increasing, and it will keep on increasing until the number of electrons that passes through my conductor per unit second, that is the current passing through my conductor, is equal to the current that is delivered by my battery. Now, let's remember some of our definitions. I will take these ones. In fact, this one. Now, if you just combine these equations, what we have is rho is equal to E over NQ times VT. Now, an object with zero resistivity or zero resistance, let's say, is an object, you can think of it as an object with an infinite drift velocity. Now, an infinite drift velocity, what it will do is, the battery gives away a given number of electrons. At the moment that the electron reaches over here, it will just go to the other side. There is no accumulation of charges at the end of my resistors. Since there is no accumulation of charges at the ends of my resistance, there is no potential difference across them. Now let's just imagine this case where we have two resistors. This has rho non-zero. And here we have another resistor which has rho equal to 0. Now the battery will be pumping out electrons. Okay, there will be electrons leaving the negative terminal, and they will be absorbed in the positive terminal. Now this zero resistance conductor, you can just imagine it as a conductor with infinite drift velocity. Or you can just imagine it as the moment that an electron reaches over here, it will be transferred to the other side. So here is the electron, but you can reach this one or this one. But the ones that are reaching this one, they instantly go to the other side. But these wires, we are also saying that they have zero resistance. So an electron here, since this has a non-zero resistance, the electrons will try to accumulate over here. But here there are no electrons, so that electron will instantly be transferred here, and it will be instantly transferred over there. So all the electrons will just move through the zero resistance. Now this instantly, meaning that it will take a very short time. And zero resistance is that it's very small resistance most of the time. So most of the electrons will just pass through this one. This is just an idealization, the zero resistivity. Yes?
Önce aslında oraya gidiyorlar fakat yani bunu ölçebileceğimiz bir süre içerisinde çok küçük bir süre içerisinde tekrar.
Well, you see, don't think of electrons as we have these very small intelligent spheres that go here and there. They just move randomly. And when you take into account the quantum mechanical effects, they also move weirdly, not just randomly. So just don't think of them as intelligent spheres. It's just randomly they move around. They just jump here and there. And the one that reaches here, it crosses this one immediately. So there's almost none passing through this one. Well, this is the easiest explanation that I can come up with. Why there's all the electrons that have zero resistance move through this one. Why we don't have the buildup of any electric field in a zero resistance conductor. Because whatever electrons that are accumulating over here, that try to accumulate over here, they move to the other side, neutralizing the lack of electrons over there. So you don't have a buildup of the electric field in a small resistance resistor. Any questions?
What about the
Strike.
yeah,
Lightning.
lightnings? If you see by a particular time, it goes to a path to the ground, but sometimes some of the parts doesn't go to the ground, and it goes like this way, and then one main path goes, but some others don't.
Well, you can think of it as it doesn't know where to go. It just tries everything. And randomly, once a path is open, for some reason, for some random reason, the other will prefer that direction. It's just like if you look at the shape, it's just like the cracks in a glass. If you just crack a glass from one end, you have this tree shape. That's basically just a random motion, random behavior. Now, again, the things I know about these phenomena are limited. I know that there is a complicated physics there, and there are whole professors working on such phenomena, how to describe such a shape. I have a vague idea. Okay, it's good that you are asking such questions. You should keep going, but you should look at different places for answers. Other questions? So let's just imagine we have this resistor. We have seen that there is an electric field that builds up in this resistor. Well, this electric field is constantly pushing the electrons. But we also said that the electrons are on the average moving with the same speed. Well, if the electrons are pushing, the electric field is pushing the electrons, it means it's doing work on the electrons. If it's doing work on the electrons, the energy of the electrons should increase. But if the energy of the electrons do not increase, so what happens to the energy conservation? Did you understand the question? We have the electric field. Here we have the resistor. Inside there is an electric field. Now, just imagine one electron sitting over here. What is the direction of the force acting on the electron? It's in the opposite direction to the electric field. So this is the direction of the force acting on the electron. Well, this is the direction of the force. So the electron will be moving in that direction. So the electric field is doing work on the electron. Agree? Okay, so there is a force, there is a displacement, so there is a work done on the electron. Work done on the electron is equal to the force acting on the electron. Let's just calculate the total work done on the electron from this point to this point, which is the length L, force acting on the electron times L. And the force acting on the electron is just Q times E times L, or Q times delta V, Q being the charge of the electron. And we also said that the electron has a drift velocity that is constant. So what happens to the energy? Well, this work done on the electron, and we have seen in mechanics courses that the work done on an object, the total work done on an object changes its kinetic energy, should change its kinetic energy. On one hand, we are doing work on the electron. This should change its kinetic energy, but on the other hand, we are saying that the kinetic energy of the electron on the average is constant. So the work that we do should be going somewhere. So where the heat. So you see what's going on. If you remember our discussion of the motion of the electron just moves randomly. So it started here, moved until this point, hit a nuclei at that point, but in a collision, the momentum of the electron has changed. So the momentum of the nuclei should change. Well, the most likely thing that will happen is that the electron also transfers some of its energy to the nuclei, to the object that it collided with. So as it is accelerating in the electric field, if you apply an external electric field, it will be moving faster. If it's moving faster in a given direction and makes collisions, it will also be transferring more of its energy. So that is where the energy goes to. So we do some work on the system by the electric field. And the work that we do on the electron, it transfers into the nuclei. So the nuclei they start to vibrate faster. But that is what we call the heat. So this much energy is used, in a sense, consumed. And that is what causes the light bulbs to light up. So it's this consumed energy, the amount of energy we give to the system, to the electron, and then the electron transfers it to either to create the heat that we heat up this room, or we heat it up further and starts to emit light, etc. So that's the energy conservation. And the amount of, let's calculate the power. Now, power is the work done per unit amount of time. This is how we define the power. Now, the power for a single electron, we said that it is Q times delta V. That is for a single electron, but we can just repeat the argument for a bunch of electrons. So this will be nothing but delta Q times delta V divided by delta T. Delta Q is the total number of electrons that pass through the wire in a given amount of time, delta Q. Delta V is the potential difference across the resistor. So the power of the resistor, or the power that this is the work done on the electron, which is consumed by the resistor, or the power dissipated by the resistor. The power dissipated by the resistor will be just delta Q over delta T times delta V. But delta Q over delta T is nothing but I. So this is equal to I times delta V. This is the power of a resistor. Now we can also write this as the power is equal to I times delta V, but delta V is equal to I times R. So this is I squared times R, or the power is equal to I times delta V, where I is delta V over R times delta V. This is delta V squared over R. Whichever one you like. Now, in the case of incandescent bulbs, not these fluorescent lamps, but the ones that get hot, this is basically the power that you give to the lamp so that it will convert it to some other form of energy. Most of the energy is converted into heat. That's why it gets hot. It will be the power that you give to the lamp, most of it is used to heat it up, and a very small fraction is used to make it emit light. And that is why the recent lamps, they can be much more efficient. They can give the same amount of light without getting heating. So what they do is they just make sure that the power that they consume, most of it is emitted as light, and a very small fraction is used to heat up the system. So that's why they become efficient. And then we can ask the question, what about the battery? So here it's the battery that gives this power, or that gives this energy. How much energy does the battery give me? Or what is the power of the battery in a given circuit? Well, basically we can do the same argument. You see, in the case of a resistor, as the charges are moving from one side to the other side of the resistor, they are crossing a potential difference of delta V. But delta V times the charge is nothing but the change in the potential energy of the system. So this is the change in the potential energy of the system, which should be transferred to the kinetic energy of the charges unless there's some other effect. But there are these extra collisions, and hence this change in the potential energy is transferred into the heat energy or any other kind of energy that the resistor converts it into. Well, if we apply the same principle to the battery, well, the battery does the same thing. It takes some charge, positive charge from the negative terminal, and puts it into the positive terminal. So it moves the charges across a potential difference of delta V. So we can say that the power of a battery it will be also I times delta V. Delta V is the potential difference created by the battery, the voltage of the battery. Okay, any questions on these ones?
What is decreasing when you use the battery?
What is decreasing? The chemicals. You are using up the chemicals. It's the chemical energy is decreasing. You are converting chemical energy in the battery, first to current, and then the resistor converts it into, let's say, heat. Yes, the battery has an internal resistance. Now let's do an exercise where we will be combining many things we have learned. Now, if you remember, we had discussed the force acting on a dielectric. You remember it? So we said that, okay, this is our capacitor, parallel plate capacitor, and we put a dielectric inside. We said that, okay, let's call this one the X. And the charge was constant. So we calculated the potential energy stored in our battery. When we calculated the U by dx, this was the force acting on the dielectric. This we had already discussed. And then some of you asked, what happens if you connect it to a battery? So the question is basically, now in this question, Q was constant. But we can just say that, okay, we connect it to a battery. Now what happens? Okay, first of all, will the force change? Do you expect the force to change? We have these two cases. One case, we have a plus Q and a minus Q in the place of the capacitor, and we don't connect it to an external battery. We just put those charges by some other means. The other case is we put those charges over there using a battery, just like in this configuration, and we keep the capacitor there. We keep the battery there. So will the force change? Should the force change? Why? Is there a new electric field? Why is there a new electric field?
When we connect the battery to the capacitor, there's a new electric field.
Why? I mean, you see, the electric field is created by the charges. The battery creates an electric field by manipulating the charges. But I'm saying that in both cases, the charges on the capacitor are Q and uniformly distributed. That doesn't change. But if that doesn't change, if the charge distribution doesn't change, then the electric field cannot change. So in both cases, we have the same electric field. So if we have the same electric field, we should get exactly the same force. So this is what I'm saying. In one case, okay, this is the dielectric is fixed over there. I connect the battery, and there is a charge plus Q and the minus Q in the plates. Okay. The other case, I don't connect the battery by some means. I just put these plus Q and minus Q over there. The charges are the same. I'm not saying that I put some random charges over there and then connect the battery. If the charges change, of course the force will change, because we had calculated that the force depends on the charges in the battery. If the charge, there is no zero charge, there is no force. But if we make sure that we create these two systems in which the charges on the capacitor is the same, the only difference between these two systems is in one of them the battery is the capacitor is connected to a battery, in the other one it is not connected to a battery. The force should not change. We should have exactly the same force. Now let's see. Do we have exactly the same force? Now, do you remember what was the force? We didn't calculate the force, right? Let's calculate the force in the absence of the battery. Now, we said that the potential energy of a capacitor, a single one, we had already evaluated it, it was Q squared over 2C, where C was epsilon 0, A over L, or 1 over C is equal to epsilon 0, no, L over epsilon 0, A, where this is our L. Now I can imagine that I divide it, I can imagine I can divide this whole thing into two capacitors, one with a dielectric, the other one without a dielectric. And if this total area, total length is, let's say, L, then 1 over C1, let's just call this part C1, this part C2, this will be L over kappa epsilon 0, kappa being the dielectric constant, and epsilon 0 is over there. Now, of course, we have to calculate the A of this part, the area of that part, but the area of that part is just proportional to x. X over L times A. Now this fraction of the total area is covered with a dielectric. So this is equal to, or C1 is equal to kappa epsilon 0 over L times x over the capital L times A, and similarly C2 is just kappa epsilon 0 over L1 minus the remaining area. Now, without the kappa. What is the equivalent capacitance of this configuration? Okay, so it's the sum, C1 plus C2. C1 plus C2, this will be equal to epsilon 0 A over L times kappa x over L plus 1 minus x over L. This is the equivalent capacitance. U is equal to Q over 2 C equivalent. The only x-dependent piece over here is the equivalent capacitance. So F, which was du by dx, this is equal to d over d C equivalent of U times derivative of the equivalent capacitance with respect to x. Q squared. Which is equal to minus Q squared over 2 equivalent capacitance squared. Well, the derivative of the equivalent capacitance with respect to x is just epsilon 0 A over L times kappa over L, large L minus 1 over large L. This is equal to minus Q squared over 2 equivalent capacitance squared epsilon 0 A over L. Now, by epsilon 0 A over L is the equivalent capacitance. No, it's not the equivalent capacitance, sorry. Kappa minus 1 divided by L. This is the force. Now, Q over C is just the potential difference across the capacitor. So the force is equal to minus delta V squared over 2 epsilon 0 A over L kappa minus 1 divided by L. Okay, of course you can just put you might go ahead and try to simplify it a bit, but I will just leave it here. Now what we did, the tricky part, we first divided our system, our capacitor, into two parts. One completely filled with a dielectric, the other one completely empty. Then this system is equal to both two of these capacitors connected in parallel. So we obtain the equivalent capacitance of my system, or the capacitance of my system partially filled with the dielectric. This is the expression. Then we can calculate the potential energy stored in my system and then just take the derivative. Now, by the way, the force is minus du by dx. That is the definition. So here I don't have this minus sign. The force is minus the derivative of the potential. Now let's look at the other way around. The other case, with the presence of the battery. Now let's see. This is again true. We can write this one. But now we need to take the derivative of u with respect to x. Now this time, since the battery, there's a battery over there, as we change X, the equivalent capacitance changes, but since the equivalent capacitance changes, the charge in the capacitor also changes. So both Q and the equivalent capacitance depend on X now. Well, you can of course calculate the dependence of Q on the equivalent on the X, but rather than that, we can write this as 1 over 2 C equivalent times V, or delta V squared, because Q over C equivalent is delta V. Now, the advantage of writing it, both are true. I mean, you can just do the calculation with both of them. But Q is a function of X, just like the equivalent capacitance, the capacitance of my system. But delta V is fixed by the battery. The battery keeps delta V constant. So if I take the derivative of this expression, it will be equal to the derivative of this expression. But the nice thing about this one is that the only X-dependent piece is over there. And that tells me that force, which is minus du by dx, this is equal to minus 1 over 2 C equivalent times, minus 1 over 2 times delta V squared times dc equivalent by dx, which will be, well, C equivalent is given over here. This is our C equivalent. So F is minus 1 over 2 delta V squared. If you take the derivative, epsilon 0 A over small l kappa minus 1 over L. This is the F. There's a minus sign. Delta V squared over 2, epsilon 0 A over L, kappa minus 1 over L. There's a plus sign. Delta V squared over 2, epsilon 0 A over L, kappa minus 1 over L. So we have two forces, but they are pointing in opposite. They have equal magnitude, but they are pointing in opposite direction. So what is wrong? Well, most of the time in your exams, when you find such results, you just erase the minus sign in some step and then say that they agree. Well, here there's another reason why these two calculations do not agree with each other. Because there's a mistake we had done. Yes? No. I mean, why should they be? Or plus Q and minus Q, they are fixed. So why should they be different? No. Okay, we can fix that sign by just ignoring some minus sign. That will fix the discrepancy. But that's not the point. The point is, where did we make a mistake? I mean, was it a mistake to choose one direction of the electric field? Do we have to change the direction of the electric field? No. So, of course, we can find a mistake, just erase some minus sign somewhere. But that's not the correct thing to do. We will be making two mistakes to get one consistent answer. So what's the mistake? Rocks is not a mistake, or scissors. So what's the mistake? So we have a conducting shell, and there's a cavity inside. In the cavity, we put a charge plus Q. So the question is charge in the inner surface well, let's say on the inner surface, and charge on the outer surface. Charge here and charge here. Now, of course, the total charge on the surface, not just at a given point on the surface. We have a conductor. Inside there's a cavity. In this cavity, we put a point charge somewhere. And then the question is, what is the total charge of this inner surface and what is the total charge of this outer surface? Not necessarily.
Conductor neutral değil mi hocam?
The conductor is neutral initially.